All right, so hello everyone. Welcome to the lecture number 12. We're actually recording it the very same day as previous lecture. So for us, it was only an hour break, but for those who watch on YouTube, it should be a week break, I guess. All right, so on last lecture, we finished with GKLS theorem with master equation, right? So it's like a form of dynamical map that the form of map that guarantees that it is a viable map, that it in principle can originate from some physical environment, but we don't care what kind of environment. We just care that we have a map that in principle is physical. The advantage of using this GKLS form is that we have there's a lot of freedom in choosing what this map actually does. So we can sculpt it, design it to fit our purposes. And this is like, and we know whatever we put in here with very little constraints, we know that this will result in a physical map, but the results it will produce can vary tremendously. So it's like opens up the whole field of study of from this mathematical point of view for in this theory of open systems. But today, what we want to focus on is a question that, okay, so mathematically speaking, the master equation or GKLS form, GKLS map, it's in principle, it's physically valid, but is it actually a good model of physical systems? And we want to show it that following from the mathematical results of Davis, who showed that this GKLS form is like an asymptotic result when you take the weak coupling limit. We want to show that even for weak coupling, but still finite coupling, it's still we can show that this GKLS form can be obtained as an approximation to probably a wide range of real environments. So in other words, we will apply our perturbation theory we developed on lecture number 10. We will apply it and just check if what we are getting fits in GKLS form or not. Okay, so the plan is, so we'll begin by the first step in our journey will be to, we will assume thermal bath. So we'll assume that the environment was initialized in a thermal equilibrium state. P E beta equal to E minus beta H E. Normalize, so trace over E minus beta H E, which we will also denote as Z, the statistical sum. Okay, probably I should write down what is the Hamiltonian. So we will use a fairly generic Hamiltonian here. So we have some bare Hamiltonian of the system. The convention is exactly the same as we used previously. 1 times HE plus the general form of coupling. So S dot, you know what, let me be explicit here. Sum over some indices alpha, we got S alpha times bare interaction operator E. And we, as we done it before, we will switch to shifted Hamiltonian, shifted system Hamiltonian, and shifted interaction operator. So we will write it like this: plus 1 times HE plus lambda alpha S alpha times F, where the shifted operators will be defined as H0S, so that's bare Hamiltonian, plus lambda E alpha trace over E, E I H E T E alpha E minus I H E T, and the initial state of environment times S alpha. But because we assume here thermal initial state, so P commutes with HE, which makes this correction to this average a constant. So this simplifies automatically to plus lambda sum over alpha trace over E alpha P E beta times S alpha. And the shifted coupling F alpha is defined as bare coupling E minus, no, not lambda, sorry, minus trace E, again, because initial state is thermal buff, thermal equilibrium, it's time independent. So this is our Hamiltonian. So this is like this general form of Hamiltonian. And one more thing, we will use this, our shorthand notation. So instead of writing this sum over alpha outer product, I will write it as like a pseudo dot product, okay? Just as a shorthand. Yeah, okay. Next thing, we will, from Davis, we know that probably if we are looking to find the GKLS form, the key will be to have a weak coupling and short correlation time, probably. So we will assume parameter regime. Regime will be, we assume weak coupling. Weak coupling, which means that lambda, so the coupling strength, times correlation time of the environment, that this is much smaller than 1, so this is small, weak coupling. And 2, we also will assume separation of timescales. Separation of timescales means that correlation time of environment is much shorter than the total evolution time and the fastest time scale in system S. So this symbols correlation time, T fast, and so on have to, we talk about them, define them in lecture number 10, I think, when we talk about perturbation theory for dynamical maps. So these are, when we consider the perturbation theory, when we think about, basically this regime, we're targeting this kind of regime. So weak coupling, short correlation time. And here we just underline that this is what we assume. And now, having said that, so we have our Hamiltonian, we shifted everything, we have initial state of environment, it's stationary, we have our weak coupling, separation of timescales, and now we will start applying approximations. Okay, now we apply the following so the strategy again, what is the goal? So the strategy that we have this we decided on the parameter regime, and now we want to follow. Okay, so what kind of approximation this regime enables us? We want to deploy those approximations and see if at the end we will get dynamical map in a GKLS form. That's the game plan. And the spoilers, we will get there indeed. But let's do it step by step. So the approximation number one will be, since we have recoupling, separation of timescales, so we'll start with something that should be called Born approximation. Born approximation. Which amounts to second order approx in for supercumulants. So it's traditionally Born approximation. It's you cut some series on second order. That's what's typically called Born approximation. So in our case, this amounts to if we have a from 1 to infinity to n integral L to K supercumulants for this Hamiltonian, and we approximate it. We cut it on the lowest second order, which means that it's minus lambda squared T L 2 U0 du, which equals to integral du from 0 to u dv. And let me pull out our contraction notation here, second cumulant of dynamical variable z. So that's a first step, Born approximation, which results in an approximation to the full dynamical map minus I lambda 0 T S F du, and we are approximating it with second order map, which is TL minus lambda square 0 TL to U0. This is what we did in the first step. So this is like what we discussed in 2 lectures ago, but with a decision made that we cut in the supercumulants on the second order, the lowest order approximation. But that's not all. Maybe 2. Second step. So before we employ actual approximation, we want to, so here we will exploit the stationarity of environment to what? To transform the supercumulant. So we have our supercumulant here, L2, du, which equals, there is a double integral here, right? U2, du1, and we have our contraction here, U2, Z, U1, contraction or cumulant, which, if we write it explicitly what it means, there are a couple of cool formulas you can use here. Let's write it like this. So there are sum over alpha 1 and alpha 2. We have our integral u1, and one of the forms that we can write it in is S alpha 2 u2. So we have this, which acts on, there is a function here that we called R. I will write in a second what it means. It depends on alpha 2 and alpha 1, and also on times u1 and u2. And it multiplies this function, another commutator, for 1 u1, plus imaginary unit, and the other function I also depends on both times and both alphas, and it multiplies anti-commutator. And just a reminder of notation we used previously. R, this is real part, of two-time correlation function of environment. So it's alpha 2f u2 times alpha 1 u1 p e beta. Okay, and I is the same but imaginary part. So this is imaginary part of same thing. Okay, so that's one of the forms you can write it in. And now this thing, environment is stationary. It means that P, the initial density matrix, it commutes with the Hamiltonian of environment. So this allows us to basically move around times in this expression, and you can then exploit it to do some algebra, which is not very thrilling. So I was thinking maybe I'll just skip the tedious calculations. And if you want to see all the details on your own, check out the notes on page 56. And I can even give you equation. So that would be equation number 261 to see all the details. I just want to skip to the final form. And when all is said and done, you move around the variables, you change the change variables from U2 and U1 to the difference of U2 and U1 and do other necessary tricks. You can transform it all into the something that looks much better. So you have integral from 0 to t over du. Then you have a super operator us 0u that acts on integral here, the v. Here we have our cumulant, which is 0 minus v contraction. And it is sandwiched in between US. And those guys, these are just unitary evolution. So this guy equals E minus I U HS bullet. Okay. And this guy then is equal to I U HS bullet. So the point of all those things we did is to, rather than having the cumulant depending on both integration variables, we managed to, using the exploiting the stationarity of correlation functions, we managed to split this integral. So now cumulant depends only on one of the times on the integral, and this is powerful because this allows us to deploy a thing that's called Markov approximation. So we take this guy, U, and we approximate it. So the heart of approximation. So look, we are assuming that time t is much longer than the correlation time, right? So this is big in comparison to correlation time. So is the upper limit of the second integral, right? Because it's capped from above by t, so it can go as far as, much further than correlation time. But what it integrates, there is a cumulant underneath, and the cumulant has effective range of correlation time, right? So if this integral goes further than correlation time, cumulant disappears, and this gives you a natural cutoff for this upper limit of this integration, right? So our approximation is like, say, okay, if this integral always cuts off on this correlation time, so we might as well just get rid of this complicating dependence on u and just stretch this integral to infinity. It will always naturally cut off at correlation time anyway. So the error we are making will hopefully be small. So this is the Markov approximation. So you take this guy and extend the limit of integration to infinity here. V, z 0, z minus v. So when we do this super operator here, it's no longer depends on time. Now it's constant. So the only dependence on time now is this transformation with unitary evolution operators. Okay. And this guy, we can write down what this what is left of this cumulant, and the form we wish to cast it into is the following. So you will have here sum over both alphas, commutator with S alpha 2, So it's just constant operator as alpha. It no longer depends on time. And here we introduce new operators, lambda minus bullet lambda L2 and take dagger of it. Okay, like this, and the closing unitary. Okay, this is the form we want for it to take. And this newly introduced constant operator, this lambda, this dreaded lambda here, this guy is defined as integral from 0 to infinity. So this is what happened with this integral we stretched. And what it integrates, well, we will have here a correlation function of environment, alpha 2, 0, f alpha 1 minus v, p e beta. And here we'll have operator S, interaction operator S alpha 1 minus V, and we integrate over V. And now, using the stationarity of environment, we can move V, to make it more pretty, move V from here to here, but not totally for free. If we move it from the second operator to first, the minus will disappear. Yes, but this minus stays here. dv. So you know, to moving the time from here to here, it is, you know, this guy. Let me just do a quick calculation. This guy is just EIHE, well, actually minus V, F alpha 1. This is the interaction picture of this operator, V, okay? And now, because the initial state is a thermal state, it commutes with HE, with Hamiltonian, so I can take this evolution operator that I have here, okay, and just move it past the density matrix, then use the cyclic property of trace to move it back from the left side, right? And then it starts to multiplying the first operator, right? But if I do this, so it's multiplied from left by this guy, right? And from right is multiplied by the remnant of the interaction picture of F alpha 1, right? So you have, so after we do this shuffling, F0 alpha 2, it changes to EIHE V F0 alpha 2 times E minus HE V, which is alpha 2V, interaction picture at time V. But this is how you exploit the stationarity, that you can move around the evolution operators. You can move them through without paying any cost through the initial state. Okay, and once you can do this and have cyclic property, you can like move around time. All right, so this is so I guess the question might be how big is the error of doing this Markov approximation, right? We had integral that's up to u, so it depends on the time u, right? And now we just said, okay, whatever we stretch it to infinity. How to estimate what kind of damage we did with this kind of approximation? Well, I have here in notes like a little bit more detailed analysis, but what I will say it here is that if you just say that, okay, my cumulant is 0 minus v, it's something that more or less roughly behaves like a theta of t core e minus v, right? So it's just hard cutoff when v is greater than correlation time, right? And you take this guy and you plug it into those expressions here. You can estimate that the error due to Markov is of order lambda t core e squared, okay, which is much smaller than 1. So the difference between between this guy and the Markov approximation is higher order in the weak coupling. So it is within our parameter regime, this error is acceptable. We are working with this accuracy anyway. Right. So now, if we were to stop here, right here, we would obtain something that's called Redfield master equation. If we stop here, we get the Redfield master equation. Redfield is a surname of a guy, again. Although I'm using red color here, it's red in the name, it's just a surname of a guy. So what is Redfield master equation? So if we define the Redfield generator, red, let's call it like that. And Redfield generator is this, would be this thing here, okay? So let's write it down what it is. So it's sum over alpha 1 and alpha 2, commutator S alpha 2, constant, so not interaction picture. And here we have lambda 2, bullet minus bullet, lambda alpha 2, dagger. Okay, that's our Redfield generator, constant superoperator. And now if we take, to get a master equation, that suggests that we have to take a look at the dynamical equation for the density matrix. So let's write down the density matrix with using Born and Markov approximations. So what is the density matrix? So we have a free evolution due to Hamiltonian of the system, and then we have a dynamical map in the interaction picture. So this is the thing we are approximating, right? S10F right, and we just approximated it with U as QTS, and here we have time ordering E minus lambda 2 integral 0 to 2 U S 0 U L red field U 0 S du. Okay, so this is, and it all acts on the initial state as 0, right? And now, when you look what's going on here, red field generator is constant, right? But it's sandwiched in unitaries. So this should trigger in you a pattern recognition. This is basically a disentanglement theorem applied to this thing. So we can reverse this, we can re-entangle this. So we can absorb the unitary in front back to the exponent. And when we do this, so we reabsorb, re-entangle the unitary minus lambda squared T L red, acting on the initial state. Okay. So now this is quite simple. What's going on here, and now we can get the dynamical equation. So if we integrate rho Ts, we are getting minus IH S rho Ts minus lambda square L red rho Ts. And this is what's called Redfield master equation. Redfield master equation. Known in literature. I'm not sure if it was before the GKLS master equation or after. I'm not sure when Redfield wrote about this stuff. However, the thing to note is that this is a Redfield master equation because this is not GKLS master equation, not yet. The generator L red, although it's constant, so we're getting closer, but it's not of GKLS form, not yet. There is one more move we have to make to actually transform it into GKLS form. So we proceed to move number 3. The move number 3. Okay. All right. So the third and final move, well, it relies on, so before we apply the approximation, first we will do another tricky transformation to our generators. So this time we'll introduce in third step, introduce something that I would call the frequency decomposition of S alphas, of operators S alpha. It's frequency decomposition, but you always have to add with respect to eigenvalues of what? Of this case of the shifted Hamiltonian HS. So let me explain what this all means. So we have our shifted Hamiltonian, right? Which is, just to remind us, is Baire Hamiltonian plus lambda sum over alpha trace E T E beta times this alpha. This is a constant operator, right? So it can have eigenvalues and eigenvectors. So let's define those guys. S A A. Okay, so these are eigenvectors or eigencats. And these guys here are eigenvalues. Energy levels, if you wish. And now, with those eigenvalues, we will define frequencies. Frequencies, omega AB, by definition, is eigenvalue SA minus eigenvalue SB. Okay, so these are our frequencies, and we do the decomposition of S alpha with respect to those frequencies. That's why the frequency in the name. So what is this frequency decomposition? Well, I think I will introduce it in implicitly. Frag decomp. Decomposition F S alpha omega. So this is how I will denote it. And you can define it like, okay, so let's start with a interaction picture of operator S alpha, which equals I S T and beres. So this is just interaction picture. And then we can, since we have eigenvectors of the Hamiltonian, we can just insert identities here and here and decompose them in the basis of eigenvectors. So we can write it as sum over AB EIH ST A S alpha and B. Okay, I just inserted identities and decompose them in bases. But these are eigenvectors, so it's very easy to evaluate what the action of the unitary here is. Just the operator will turn into the corresponding eigenvalue. So this turns into sum over AB E I T H HSA do I introduce the notation? And let's pick a symbol for AB for the matrix element of S. And here we have B E minus I T H S B. Okay, now they are numbers. The exponents are numbers. And so we can collect them into one exponent, no problem with that. But if I do that, I get H of A minus H of B, but that's a frequency omega AB. So I have here time-dependent factor and then operator here. AB. And now one more thing we can do here. Make it a sum over omega I omega t sum over AB delta omega AB A S A B alpha B. Okay. And now this thing here, this is what we will call S alpha omega. Okay, so this funny thing. Things to note here. is S of minus omega alpha equals S alpha omega dagger. So the frequency decomposition, those components are non-Hermitian. Taking a dagger equals to flipping the sign of a frequency. Yeah, so this is a thing to note. What is cool about this, what is good about this frequency decomposition is that, I mean, you can see it from the very definition that it's a interaction picture, or whenever it meets unitary evolution generated by the Hamiltonian, it's very easy to compute what you get, right? Because, because of this decomposition into eigen projections on the eigen states of the Hamiltonian. So having this frequency decomposition is a very good trick to have in your back pocket. It comes in handy often. And now we start deploying it. So first use S omega alpha in operator of lambda. So we will deploy it inside lambda. So when you do it, what do we get? F alpha 2 V H F alpha 1 0 P E beta. And here we have here we should have S minus V alpha, right? But we can use our frequency decomposition here, right? We have it right over here, right? S interaction picture is decomposes into sum over omegas and so on and so forth. So we can transform this guy into sum over omega integral trace E F alpha to V F alpha 1 0 P E beta E minus I omega V dV. So we get here a half of the Fourier transform times the frequency component of S. Right, this is almost Fourier transform of the correlation function, but it's only half of it. So not exactly Fourier transform. But we will anyway give it a name to this coefficient. I will call it G alpha 2 alpha 1 of omega. Right? So this half of Fourier transform correlation function, I call it G. So this is what we get for lambdas, and we use it further to also transform the supercumulant we got from previous step. So we get U0S L Redfield generator. So this is 0U U0S du. And now, again, to properly deploy this decomposition, there's a lot of algebra involved. I don't want to write it down here, okay? Because it will be super annoying and it's not very illuminating. So if you want to know details, that's equation 270, okay? Page 58. If you want to know all the slope details here. But if you want to know the final result, I will write it to you. So we'll have sum over alphas, and we will have sum over omegas, omega 1 and omega 2. So we use our tuple notation. Open parentheses because there will be a lot of terms here. We have our coefficient G, alpha 2, alpha 1, omega 2, S omega 1, alpha 2, dagger, S alpha 1, omega 2. So that's 1 and bullet here on the right side. Then you minus G alphas omega 2, S alpha 1, omega 2, bullet, S omega 1, alpha 2, dagger. Two more terms. I'm getting to a point here. Don't worry. Omega 1. So complex conjugate. Alpha 2, omega 2, bullet, S alpha 1, omega 1, dagger. And last term, S alpha 1, omega 1, dagger, S alpha 2, omega 2, G, complex conjugate, alpha, omega 1. Okay? What happens with time? This is why we introduced the frequency decomposition in the first place, because now we are able to confine all the time dependence into one phase factor. This is why we did it. This is why you introduce the frequency decomposition. So you start with you start here where you have time dependent operators. Everything is rotated with this in this interaction picture. By doing this frequency decomposition, you take all this time dependence and plug it into this relatively simple form factor. And you have a billion of terms here. 2 omegas, 2 alphas, different configurations, different coefficients. Everything looks nightmarish. However, and this is where we can finally get to the approximation, the last approximation we need when you have this form. So now notice if you take on resonance terms, when omega 2 equals omega 1. Because we have here sum over all omegas, and there is a class of terms where omega 2 equals omega 1. If you do this, then this phase factor simplifies greatly, right? Because you get, it's just T. Just linearly, it's just T, right? Versus off resonance terms. When omega 2 is not the same as omega 1. What do you get then? EI omega 2 minus omega 1. Well, this is quite simple integral to perform. One of the forms you can write it in is 1/2 omega 2 minus omega 1 t times sinc omega 2 minus omega 1 t divided by 2. Sinc function is sinc of x is just sine x minus x. Okay. Minus x. Oh, sorry. Brain fart. Divided by x. sinus n divided L. So this function, if you want to imagine, sinus x is just sinus, everyone knows how it looks like, but sinc is around 0, it has a peak, 1, and then it's symmetric, and it drops off as 1 over x. Okay, so it's a decaying function. So in other words, if you compare off-resonance terms, you compare them with on-resonance terms, I0 du, right? So you get something that you get sinc omega 2 omega 1 t divided by 2. And this guy here, when t is large enough, or you say omega 2 minus omega 1 times t is much bigger than 2 pi, this guy goes to 0 essentially. So what it means is that because on-resonance term scale linearly with time and off-resonance terms don't, for sufficiently long times, on-resonance terms win and they overshadow the off-resonance term. Okay, so, and this is a basic idea behind something that's called either secular approximation, or sometimes called rotating wave approximation. Rotating wave approx. So secular approximation or rotating wave approximations amounts to looking at this expression we have here where there is a sum over all the omegas and just neglect everything where omega 2 is not equal omega 1. You leave only diagonal terms which scale linearly with time, which scale as t. And you just leave them in, the rest go to hell, go to 0. This is a rotating wave approximation or secular approximation. So in this way, you will get U0 S Redfield U0S du. We approximate it with t times sum over alpha, sum over omega, but only one omega because we are keeping only diagonal terms. And you can rearrange those terms in a clever way, which I will do here. So you can write all of this as 1/2 times g alpha 2 alpha 1 omega minus g alpha 1 alpha 2 omega complex conjugate, and commutator with s omega alpha 2 dagger s omega alpha 1 bullet. This is one term. Sorry, I have to go to the next line, plus g alpha 2 alpha 1 omega, this time plus g alpha 1 alpha 2 complex conjugate omega. And superoperators we are left with here is 1/2 anti-commutator s alpha 2 omega dagger s omega alpha 1 bullet minus as omega alpha 1 bullet omega alpha 2. Oop, and close parentheses. So to have this approximation working well, well, you have to, t has to be long enough, okay? So there is, you can find it has to be long in comparison to what? Well, it's not so difficult to find, because you need like basically find the least, the most problematic combination of omegas. So that is the smallest one. So take mean over omega 2 different from omega 1, omega 2, omega 1 times t, which we can call as 2 pi t divided by the slowest time scale in S. And this guy has to be much longer than 2 pi, which implies that t must be much longer than the slowest time scale in our problem. Okay, so t is long enough, you will get there where the secular approximation kicks in, and you get this guy here. So do I want to take a quick and dirty break? Yeah, let's take 10 minutes break, and then I will continue, because we are almost there. Okay, so let's continue. So this was secular approximation is the last approximation. The rest, so we already got GKLS form. Now it's up to us to actually identify it, because we have this monstrosity here, a lot of terms, a lot of sums. There are some structures that might kind of resemble something. In GKLS form, there was this anti-commutator term and the sandwich term and the commutator term, but there were a couple of conditions on the operators inside there. One should be Hermitian. There was some matrix that's supposed to be positive. So we just have to extract the info from this mess here, okay? So approximations are done. Now we just identify stuff. And now the biggest hurdle are those coefficients here. This is just what's going on here. However, there is something that is going on here that has a structure, because you see, you can these coefficients g alpha 2, alpha 1 of omega, you can treat them actually as matrix elements, as elements of a matrix that's block diagonal in index omega. Let me explain what I mean. So if I defined, let me erase this, let's not confuse that. Let me define a matrix G. It's supposed to be boldface, matrix boldface font. That is, I will define it as a matrix made out of, so it's block diagonal in omegas, but in alphas is just, it's not. Okay, so this is a matrix made out of those coefficients here. So in other words, if I take then G alpha 2, alpha 1 of omega is then nothing else but taking this matrix and taking index alpha 2 omega, alpha 1 omega. So it's a compounded index. It's like two parts, right? But it is a matrix. Quadratic matrix is just diagonal in this omega part of index. Okay, does it make sense what I'm saying here? So I just take all those coefficients plus deltas and arrange them in a matrix, and I call it G, underline, underline. Right? So that the element with index alpha 2 omega and alpha 1 omega equals the coefficient, the original coefficient. But if this is this coefficient, then the other coefficient, because if you look at this formula, those two coefficients always come in pair, right? You have G alpha 2 alpha 1 omega, and there is partner G alpha 1 alpha 2, so the flipped alphas, omega complex conjugate. You know, these here they come as a difference, here they come as a sum. So we decipher or parameterize one of them. So what is the other one? Actually, G alpha 1 alpha 2 omega. This will then be, you take G, dagger it, and take element this index. Not because the dagger, right? Because what dagger does? Dagger does transposition and complex conjugate, right? So if I take G dagger and take alpha 2 omega, alpha 1 omega, I get coefficient where the transposition gives me the reverse order of alphas, okay? So this is, I notice this thing that I can do, this trick. But what it means for us, now if we get those two combinations, the difference and the sum, so if I take G alpha 2, alpha 1, omega, plus G conjugate alpha 1, alpha 2, omega, using those two relations, okay, then this is nothing else than G alpha 2 omega alpha 1 omega plus G dagger alpha 2 omega alpha 1 omega. Or in other words, this is G plus G dagger alpha 2 omega alpha 1 omega. So this combination is actually a matrix element of matrix G plus its Hermitian conjugate. And of course, the other one, the difference, minus G, alpha 1, alpha 2, omega. This will, of course, turn into G minus its Hermitian conjunction, its dagger. All right. And now, what this actually gives us? You see, if G is some matrix with some form, you know, it's block diagonal, but that's it. But G plus G dagger, it's Hermitian, right? Because you take dagger of G plus G dagger, you get G plus G dagger, right? The difference is anti-Hermitian. Means if you take a dagger of this difference, you get minus the difference, which makes, so G plus G dagger Hermitian, and I imaginary unit, G minus G dagger, also Hermitian. Because G minus G dagger is anti-Hermitian, you multiply by I, it gives you Hermitian matrix. Okay, so why is it relevant? There are two reasons why this is relevant. So one, if we take this whole beast, okay, and rewrite this commutator as minus I commutator sum alpha sum omega I G alpha 2 alpha 1 omega minus G alpha 1 alpha 2 omega star S alpha 2 omega dagger alpha 1 omega alpha 1. Okay, so I will quickly flash just to explain. So I had here this S dagger times S under commutator, so just took all the numbers and just plug it in here under the sign of commutator, and I multiplied it by I times minus I, which is 1. Okay, so I get this then. So this here, this guy here is some operator. So this is some operator. I'd say it's some operator. Let's call it H, right? So now the question is this operator Hermitian or not? Well, because we now know that this guy here, this combination of coefficients, is actually I G minus G dagger alpha 2 omega alpha 1 omega, which is a Hermitian, which is a matrix element of a Hermitian matrix. We can actually show that this thing here, this whole sum, this whole beast, is actually Hermitian. So we can show alpha 2 omega I G minus G dagger alpha 2 omega alpha 1 omega S alpha 2 omega dagger S omega alpha 1. But when you take a dagger of this guy, you just get it. You get it back. Alpha 2 omega alpha 1 omega. Okay, so this H guy is Hermitian, and I will spare you the couple of lines of algebra to show it, but once you know that this thing here, this matrix here is Hermitian, then, you know, taking a complex conjugate allows you to transpose it and stuff like that, and you can use this to with using some, you're renaming the indices and stuff like that. You can show that it's, when you dagger it, you actually reproduce it. So it's Hermitian. This H here, I lost my cursor. It's actually H dagger. It's actually Hermitian. So that's one. Because if you remember, GKLS form had one of the operators there had to be Hermitian. This will be this operator actually. But there was the other thing. There was this matrix there that had to be positive semi-definite. Okay. So we covered here the difference between G and G dagger, which sat here, and now we have a sum. Okay. So we can actually show that this sum, that this G plus G dagger, we can show that it is actually positive semi-definite matrix. And to demonstrate it, I think I have to write some stuff, sorry. Because there is actually some physics going on here. It's actually positive thanks to physics. So let us check if this G is positive. So to check if a matrix is positive, one of the methods is to take the average value on some vector of this matrix, right? So you would have to, if we define for us a vector x, which would be a column made out of coefficients alpha, okay? And then we would take xg plus g dagger times x. Well, probably dagger here as well. Okay, so this is like the cat bra average value of the matrix of the operator. So it's enough if we consider this in because g plus g dagger is block diagonal in omega, so it's enough to consider each block independently. So we just pick one of the blocks, one of the omegas, and we look at this this expectation value, which equals to sum over alpha 2 and alpha 1, x alpha 2 complex conjugate, g alpha 2 alpha 1 omega plus g alpha 1 alpha 2 star omega times x alpha 1. This is what it means. But x are just, you know, some whatever unspecified numbers here, complex numbers. And we want to show, if we can show that this thing here is it's non-negative, we show that the matrix is positive semi-definite, or in other words, that its eigenvalues are all positive, or non-negative at least. And how come is it so? Well, we have to put in what G means, actually, to make any progress. So we have sum over alphas, x alpha 2 star x alpha 1. And what are those G's? Those, they were half of Fourier transforms, if you remember. So the first G is trace f alpha 2 v f alpha 1 0 beta ei minus omega v dv, okay? And the other one, it's also half of the Fourier transform, but the alphas are flipped, and we have a complex conjugate. So alpha 1 this time, alpha 2 0, p beta hat, complex conjugate, so star here, I omega v. All right. Now the trick for future, maybe you will use it someday. Maybe you will find a situation where it will be useful. Stuff like that, which happens a lot when you are checking for positivity of something, which is it happens too often to be. It happens really often, checking for positivity of some matrices. The trick is that to absorb the sums over x. What I mean by that. So let me rewrite it as trace, but now sum over alpha 2 f alpha 2 v time x alpha 2. Okay, so I just gobbled up the sum. And the same thing with the other sum. Star. So star. Alpha 1, x alpha 1, f alpha 1, 0. P E beta. Okay, whatever. It's cool, it's cool. EI minus omega V dV. And similar thing with the other one, trace E. But the other one has there is a complex conjugate on the trace. So we have to take this into account, which actually leads us to symmetric expression. X of 1 V P beta star. Oh yeah. I can get rid of star. If I write it like this, I can get rid of the star. I can use star to exchange the order of operators under the trace, and I can use also the what the S used here, and I can change the names of variables if I want to. So from alpha 1 to alpha 2, and I think I did it here. Oh, what did I did here? Okay, the next step, I did something here. I don't remember exactly what it was, but it should be correct. The last thing I can do here is to change variable v, change the sign of variable in the second integral to actually flip everything to sum both integrals into one integral. X alpha 2 Yeah, okay. So now I have something like this. And now the trick is, sorry, this is 0. The trick is to recognize, that this thing here, you can treat it as just a new observable, alpha x alpha f alpha. Okay, it's just this combination of f's. We just call it, oh, this is just a new observable, and then what we get here is a Fourier transform of a 2-time correlation function of this new observable x. Okay, but this is a thing that we actually encountered previously. This is the Fourier transform of correlation functions was something when we discussed Gaussian approximation and fluctuation dissipation theorem. Okay, so we can actually use fluctuation dissipation theorem here because our initial state is a thermal equilibrium, and we can transform this guy here into the following form: 1 minus E beta omega minus 1 E beta omega plus 1 times the Fourier transform of a real part of this correlation function. GV, which in the end can be, this thermal factor in front can be simplified to just E beta omega plus 1 in denominator, and the Fourier transform of a real part of a correlation function is something I hope we already said this, of something we call spectral density. So this guy here, this would be a spectral density of observable X frequency omega. Okay. So this is like physically relevant thing, and this coefficient here is obviously positive, it's non-zero, and the spectral density, there are two ways of showing that it is also non-negative. One, you can just invoke a proper mathematical theorems to show this, that this kind of expression has to be non-negative. But there is also a physics-based argument here. You can show that if spectral density of some observable in some system at temperature beta could be negative for some omegas, you would be able to construct a device that would violate second law of thermodynamics. You could just make entropy shrink rather than increase. So there are some interesting constructions where you use some frequency filters and you filter power from some signal, which then, everything's expressed through spectral density. Then the transfer of power is expressed through spectral density. And if it was possible to find a frequency for which spectral density is negative, then you could just filter for this specific frequency. And from there, you could build an engine that just decreases entropy, which would be, not good. So there is a mathematical proof, but also a physical proof, which is neat, I think. So this whole thing is non-negative, which means that this matrix is also non-negative, or in other words, its eigenvalues are non-negative numbers. So having said that, we can wrap this up. So we made 3 steps of approximation, starting from Born approximation, where we cut a supercumulant series on the lowest second order, right? So we get things that we discussed a couple of lectures ago. But then we said, okay, we can do more with that. We took the remaining supercumulant, which was a integral of some L2, of basically a double integral of a second order cumulant of a dynamical variable. We use the fact that there is the environment is stationary. We did some algebra, blah, blah, blah. We changed change the variables of integration. And then we went to Markov approximation. When we took one of those integrals, time integrals, and pushed it to infinity, so that we got effectively a constant operator. So that was Born plus Markov. If we stop there, we got Redfield master equation, which is not of GKLS form. So then we went to third step, where we did this frequency decomposition. so that we confined all the time dependence in our generators to phase factors. And then we said, okay, there is a difference between on resonance and off resonance terms, which allowed us to deploy the secular approximation or rotating wave approximation, where we kept only on resonance terms. This led us to this form. And now we recognize that this thing here is Hermitian, and this thing here is a positive semi-definite matrix. In other words, we are now at, so we're done with approximations, and we are at secular Born-Markov approximation, which gives us that our Ts times F, our dynamical map, let's just write it in a full glory, just to have to have everything in plain sight. So we have our approximation when this is approximated by minus lambda 2 T L DAF, a generator L DAF for Davis. And this generator L DAF is defined as minus I 1/2 sum over omega sum over alphas. We have here I, our matrix G minus G dagger element alpha 2 omega alpha 1 omega S alpha 2 omega dagger S omega alpha 1 no dagger commutator, and we know that this guy is Hermitian. So that's the one part. There we have plus sum over omega sum over alpha. We have G plus G alpha 2 omega alpha 1 omega, and it multiplies 1/2 anti-commutator alpha 1 bullet minus a sandwich. Dagger. So this is what I will call Davis generator. And it is of GKLS form. So we can say that minus lambda square L DAV actually equals L GKLS when we made the following identifications. So maybe I would jump to the GKLS form just for reference. Oh, it was really up there. So GKLS form was that there was this minus I commutator with H, and H is supposed to be Hermitian. So we got this guy. Then there's the other term where you have sandwich and 1/2 of anti-commutator of jump operator dagger times jump operator, and everything, there is a matrix G, which is supposed to be positive semi-definite. So we have our Davis generator. So now all that's left is to make an identification. Which operators correspond to jump operators, which coefficients correspond to this positive matrix, and what is H. And we kind of, we know what's up. So we have this H from Davis This is what corresponds with this. This guy is here. So actually minus 1/2 omega alpha Ig minus G dagger alpha 2 omega alpha 1 omega. Okay. Jump operators, L mu. Well, they are simply our frequency decomposition, S. It's just a composite index. So mu corresponds to omega and alpha. And G mu nu, well, that's also very simple. This is our matrix G dagger with also a composite. Well, actually, probably times lambda square also, and here lambda square as well. What is it? Yeah. Boom. So this is the end of the journey. We managed to do it. So to reiterate, so we have this Gekales theorem. The question was, is this Gekales form good for modeling actual systems? And we just showed that you take some system with short enough correlation time and weak enough coupling, and just a natural consequence of applying reasonable approximations, you get to this Gekales form with jump operators corresponding to the frequency decomposition of the system side coupling operator. You have this H, this shift of Hamiltonian, that's something, some monstrosity, and the coefficient, this G, this matrix G, is related to just to remember the G guys, alpha prime omega. This was like a half of Fourier transform of correlation function of environment side decoupling. TV. Okay, just to recall what the G is. And what else? Finishing touch, I guess. I have here an assignment, which you might look at. It's 33. Let me check, because I'm doubt. I have my doubts. It's number 33. No, it is. Okay. Okay. So assignment 33 is a simple one, to be honest. Just show that the Davis generator actually commutes with the Hamiltonian, with the shifted Hamiltonian, or to be more concrete, thing like that. When you take this kind of sandwich of superoperators, you just get L Davis. Okay. And this is a direct consequence of us using the secular approximation, that everything is like diagonal in energies, in frequencies. And once you show this, you can write down the master equation. Davis master equation. Davis master equation for the density matrix, rho st equal to minus I hs rho ts minus lambda square L Davis rho ts. Okay, that's a master equation. Very good. So that's the story behind master equations. The thing, maybe a small comment, meta comment about this stuff. So for us, the way I approach this course from this first principles approach, right? I was interested in like describing the dynamics in the open system by deriving the dynamical map by looking at the actual environment underneath, right, from first principles, right? And this led us to basically culminated in the story of computability of the dynamical map. We had those supercumulants, perturbation theories, and so on and so forth. Traditional approach to this kind of course would be to actually start with GKLS theory, with CP maps. People will say, oh, open system dynamics, oh, this is described by CP maps. That is a super operators that have Krauss representations. And then they will go to this time-dependent Krauss operators. They would postulate, oh, let's consider this simple maps that satisfy this very simple dynamical equation with constant generator, which by the GKLS theorem has to have this specific GKLS form. Then they will talk about, they will try to show that there is this Born-Markov plus secular approximation to show that this model is actually valid and that it describes real systems. So you will end up here, basically, at this point, and this would be where the course starts, with some examples and so on and so forth. So we did something unorthodox here, because we are like finishing with this complete positivity and GKLS stuff. Because for us, primary approach was this first principle stuff, not the FX oriented stuff. But now that we are here, we have this master equation. I would like to do something with it. Okay, to finish off or to approach the end of our journey. We still have like maybe 15 minutes. Okay, if you can. Just to give you a primer for what's to come. So what I want to do with this stuff, so I want to move to next chapter, 6, dynamics of thermalization. What do I mean by that? Because there are, scenarios where you would try to deploy the open system theory. They are numerous, and there are many contexts where you might try to do it. But there are a couple of like topics, couple of contexts that seems like the theory of open systems should give us some like a universal story about some important physical processes. One of those processes is what I call thermalization. That is the thing that we are taught from the very first year, and that is very intuitively feels intuitively correct. That if you have a system, a thermal bath, temperature beta, thermal bath. thermal bath. And you bring in some small system S, and you let those two interact, right? Then over time, the state of S should thermalize. Okay, that it should approach state of thermal equilibrium, which would be, so you get something that's proportional to E minus beta, which beta is the same temperature as the temperature of bath, and some operator representing the energy in our system S, right? This is like this is the fundamental, the whole thermodynamics and statistical physics is built around this, the assumption that this is how it works, right? And now, of course, system S, from point of view of open system theory, this is like a perfect opportunity to deploy our theory, because we have our system S, we are interested in evolution of its state, and we have here a bath, which is an environment for our system, right? Moreover, typically people think of thermalization in the context when this coupling here, this is weak. But you want to think about thermalization in the context of weak coupling as well. Also long evolution time, because you want thermalization to occur when T goes to infinity, right? You don't care about the transient stuff, what happens in between. You want to just see that eventually, in the end, we will reach this equilibrium state with the temperature same as the thermal bath. So this thing, the process of thermalization, the dynamics of it, should be described by our theory of open systems. And because we can focus on the context of weak coupling, maybe even we can use this whole GKLS or Davis approximation here, right? So something to analyze. And so on the next lecture, because I want to let you go now, I want to break down this whole process, describe how it happens actually, not just saying that, oh, it will eventually thermalize, but actually to check how it looks like and when it actually, what are the necessary conditions for it actually to occur? Because we believe that it's a kind of robust process, but surely there are some exceptions. And our theory should allow us to actually get a glimpse into the dynamics and actually see what is necessary for it to occur. And yeah, and then to learn some maybe interesting physics along the way. So that's the teaser for the next lecture. All right, so let's end it here.